Sir, can you able to see my screen?
Yes, sir. Yes. The screen is visible, sir.
Okay, sir.
Yes.
Thank you.
Yes, sir. Visible, sir.
Thank you, sir. Thank you. So, my talk is today the introduction to electric vehicles and fuel cell technologies for sustainable mobility. We needed to understand. I started with the importance of hydrogen technology. Now we need to see that the fuel cell electric vehicle versus the battery electric vehicle, how it is supporting for sustainable mobility. To support the transition process to sustainable mobility, the fuel cells are introduced to be used on electric vehicles where the vehicle battery is reached by hydrogen present in the tank. So a battery electric vehicle uses an onboard battery pack to power the vehicle motor, which includes varying configurations of battery cells. Despite the environmental and efficiency advantages of battery electric vehicles, as Principal Sir said, lithium-ion batteries only have approximately 1% of the energy density of petrol and diesel. So for this reason, smaller and lighter vehicles appear to be the best candidates for the battery electric powertrains. As vehicles increase in size, the size and weight of the battery pack are required to power the vehicle, as well as the available range begin to make the battery power a less attractive option. So the hydrogen fuel cell electric vehicles have a far greater energy storage density than lithium-ion batteries, offering a significant advantage for electric vehicles in terms of range. So also being lighter and required less space. So therefore, the fuel cell technology can lead to the advantage of overcoming negative aspects such as a range anxiety, because EV equipped with fuel cells show greater autonomy and lower charging time than electric vehicles. So in addition, there are economic advantages to use the fuel cell electric vehicle, since it is estimated that lithium-ion battery charging and discharging at 1C, that is 1 hour, as a cost approximately $130 per kilowatt hour in terms of power output. So on the contrary, compressed hydrogen tanks and fuel cell stacks respectively cost approximately $15 per kilowatt hour and $53 per kilowatt, the model based like that. So further, it is also estimated that a hydrogen price at the pump are reduced. So these are some information related to the cost aspects. So we just want to discuss, started with the overall efficiency when you are using with a fuel cell, how much it will be. So for example, if you are taking with the two technologies, the fuel cell technology and the battery technologies, so the overall efficiency of the fuel cell is around 30%. The current cost is $53 per kilowatt. That is a technological cost. So 0.24 US dollar per kilowatt, that is a refueling cost, and this is the and refueling time also we need to see that it is less than 10 minutes. The range of autonomy is up to 600 kilometers. The energy density is 550 watt hour. Then sustainability is a common and safe material, except for platinum. But a battery is around 75% of efficiency.
Sir, there's no slides are not
Changing.
Okay. I have not moved with the slides. I just want to give the introduction. So the battery technology nowadays we are using extensively for EV applications. So coming to the introduction, with respect to the EV technology, an EV electric vehicle is a vehicle that operates on electric motor instead of an internal combustion engine that generates power by burning a mix of fuels and gases. Electric vehicle is seen as a possible replacement for the current generation automobile in near future to address environmental challenges. So we can observe that the EV technologies, so inspired by road going automobiles powered by electricity, propelled by one electric motor or more using batteries. Electric motor give instant torque and smooth acceleration. Plug-in vehicles are fast, fun and efficient. Maintenance is simpler and cheap. So actually, in our institute, we are working more on EV technologies. So particularly the battery technologies. So we can observe that in terms of the overall efficiency of the vehicle for battery electric vehicle, the efficiency of the battery and the transportation and the distribution can reach around 75%. For fuel cell electric vehicles, several steps should be considered, such as electricity, electrolysis, comparison, transportation, and distribution. Therefore, despite of the fuel cell efficiency, approximately 40 to 60%, the final energy efficiency of the vehicle is estimated to be approximately 30%. So there are also a technical challenge that fuel cell electric vehicles technology are facing, which must be considered, such as availability and clean protection of hydrogen and utilization of the hydrogen as a power source. This and all the research aspects. So the production of the hydrogen requires a significant amount of energy. So that also is there. So we just want to see that with respect to the ecosystems, with respect to the electric vehicle applications. It involves with the information, money. Government has given many subsidies for purchasing the EV vehicles, and we need to see that information, money, and electricity. So the major trends and the key players, one can see that the major trends with respect to the EV technologies are electric vehicle information, a lithium-ion battery, renewable power, smart grid, grid storage, then the vehicle to building operation, or grid operation, smart charging, those things it will be coming to the picture. Whereas the key system players that indicates with the consumers, data flow, insurance, R&D technology, climate change, and the policy. This and all we need to see that. And with respect to the timeline of the EVs, you can see that it is started with the 1801 only, that indicates with the Faraday's law. So then it is started with 1832 only, the first electric motor capable of rotating machine, followed by many technologies where came. Right now we are in here. So the present day sales of electric cars are topped with 2.1 million globally in 2019. By 2030, the electric vehicle technology goal is for 50% of the vehicles on the road to be the alternative energy. And coming to the history of electric vehicles. So it is started with the 1837, the electric car being their long history in Aberdeen, Scotland, through inventor Robert Davidson. So later in 1841, these are some histories. So after the more than 40 years, the inventor Thomas Parker creates the first manufacturing electric automobile in London, then followed by the car is a little more than an electrified wagon. So this 6-seater has top speed of 14 meter per hour, and coming to the people, I mean, during inauguration, many of them, they are talking about the pollution. So coming to the air quality in Indian cities. So this source is taken by the Hindu. Here you can see that the estimated deaths and the estimated cost. So here with respect to the Delhi, Mumbai, Bengaluru, Hyderabad, Chennai and Lucknow. So we were seen here 22% out of the more than uh, 30 most polluted cities in the world are in India. The 41% of NOx emission in Delhi were due to vehicle in 2020. 23% of PM 2.5 emission in Delhi were due to the vehicles in 2020. So coming to the carbon emission, here very clearly we can observe that. So the technology and advancements, the advanced internal combustion engine, the carbon reduction potential is only 15%, whereas natural gas and biofuels is 10 to 30%, and electrification is like a hybrid fuel cell and electric vehicle, then a fully electric and hydrogen. So you can see that very clearly we got the advancements with respect to the carbon emission. So here I just want to discuss about the electric vehicles, since our students are working more on electric vehicles and power electronic technologies. I just want to give some introduction about the concept of electric and hybrid electric vehicle. In a traction system, one can consider that electric vehicle or hybrid electric vehicle. How it will be it can be the single source or multiple source. So like a fossil fuel in a battery, fuel cell like that. So it may be the single or multiple energy converter, like a chemical, mechanical, electrical like that. So mechanical coupling under transition. So that also is there. So from the diagram, it is very clear. You can see that first energy source, it is supplying to the energy converter, then it is fed to the load. Here the load is an electric vehicle. So similarly, sometimes it may be the bidirectional also. We can use the energy converter too and energy source too. So here we can understand the importance of the bidirectional power flow, why it is required, when it is required, those things. So coming to the types of electric vehicles. So it can be, we can say that a battery powered electric vehicle, series hybrid electric vehicle, parallel hybrid electric vehicle, series parallel hybrid electric vehicle, plug-in hybrid electric vehicle, like that. So the battery powered electric vehicle is a battery electric vehicle is propelled by electric motor. So only energy source only is taken as on board, that is battery. The advantage is zero emission. So everybody is talking about this one. That is why government is also promoting to use the electric vehicle, simple structure and control of the traction system. So coming to the types of electric vehicles. So the battery powered electric vehicle, the electric machine. So the electric machine or electric motor delivers a mechanical power to the load, and the electric machine, it may act as a generator or motor. So this is the one of the generalized structure. Here you see that the source we can use it either the multiple source or single source. Here in this diagram, it is shown with only battery. So here you can see that the battery is feeding power to the power electronic converter, then electric machine, and feed it to the load. So the thick line is also represented and the thin line is also represented, I mean the dotted line, that indicates with the power it is flowing both the directions. So that means your power electronic converter, it has to support in both the directions. So coming to the series hybrid electric vehicle, here you can see that we are using IC engine also, the IC engine and electric generator energy source one, and a battery also we were using. So here also we are using one power electronic converter. Here also we are using one power electronic converter. Through this, we are feeding power to the electric machine, and we are feeding power to the load. So this IC engine, it will be acting as a generator. And the power, it may be the bidirectional for the battery, whereas here it is only unidirectional with respect to the IC engine. So coming to the powertrain and attractive characteristics. So the engine, like it consists of a battery and a motor. So that output of the motor is the mechanical energy that we are feeding to the machine. I mean, the feeding to the load through transmission, the clutch or a torque converter, then differential. So then only the power, here only the power it is transmitted to the wheel, that is a driven wheel. So through the driving shaft. So the torque on the driving wheels, which is transmitted from the power plant, we can express by fundamental equations. The tractive effort on the driven wheels can be expressed by this equation, torque by speed. So here the translational speed of the wheel center that we can represent it like this. So the drivetrain, when you are referring the energy source, electric motor, mechanical translation, then it is the energy is transmitted. Here in this, we need to understand where it is a mechanical link, where it is a electrical link, where it is a control link. So here you can see that the mechanical link, it is very clear here only. So this symbol represents with the mechanical link. And the electrical link, where it will be electric power converter, then electric motor, then the controller. So the controller is a vehicle controller. So the way through the vehicle controller only we can say that like energy management unit, then the vehicle controller, then in addition, the energy source, how we are managing. So this is the represents with the energy source subsystem, and this one is the represents with the auxiliary systems. So that is where the power which is used for the other operational aspects. So for example, auxiliary power supply, and then a power steering unit. So hotel climate control unit, and this is called as auxiliary subsystems. So now coming to the technologies. So the drivetrain and the possible EV configurations. So one can see that here M represents with the motor, and GB represents the gearbox, and C represents the clutch, and D represents the differential, and FG represents the fixed gearing. Here you can see that the EV configuration with the clutch and the gearbox and the differential is also there. This is one kind of technology. The another kind of technology is we are using two motors, but we required the synchronization. So, and we are having the fixed gearing, we can connect it like this, that also possible. Then we can have, this is the EV configuration, mechanical differential is replaced by two electric motors, here one electric motor. And the third configuration, this represents with the EV configuration without clutch and gearbox. So like a machine, the fixed gearing and a differential. And the fourth configuration is the EV configuration with the wheel motor and a mechanical gear. So here you can see that the machine directly attached. So such kind of hub motors you can see in practice. And EV configuration with the fixed gearbox and the differential also there. So like this. Then the EV configuration within the wheel motor and no mechanical gear. So that also possible. So this kind of configuration, you can find it with respect to the two-wheelers, whereas this kind of configuration and this kind of configuration, you can find it out with respect to the four-wheelers. And coming to the electric vehicle battery charging system, I just want to show you here some case studies which we are executed in our laboratory. So here you can understand that the electric vehicle battery charging system, how it will be. So the battery is an important source. So how it will be charged? So for example, the electric utility is there. That electric utility, it will be fed to the, that is the AC supply, it is fed to the power electronic converter, that is the AC to DC power converter. That DC, it is fed to the DC-DC converter for charging the batteries. So it may the battery charging, it may be the slow charging or fast charging like that. Many researchers, they are focusing towards the battery monitoring, control, management, then the improving the efficiency. So many aspects of people are working in this area. So we require a control system properly to control the power converter like a AC-DC power converter and DC-DC converter. The main role of the AC-DC power converter is to maintain the unity power factor at the source terminal, and the maintaining the DC link voltage is also taken care by the AC-DC converter. That means the sinusoidal current shaping and the unity power factor, it is and DC link voltage maintaining constant, that indicates with the AC-DC power converter. Then the charge, it will be controlled. Basically the charging of the battery, it may be the constant voltage charging or it may be the constant current charging, whatever it may be. So according to the method which we are preferring, we can use it with respect to the power electronic controller. And AC grid. The AC grid is like the power which we are transferring from AC grid to DC. So the detailed diagram, it will be represented here. You can see that the power, it may be the unidirectional also and bidirectional also. When it will be, that we will discuss further. So we are working towards the charging of the batteries only. So according to the some standards like 196, 62196, 61851, 15118, charging is classified into various types according to the power level, safety communication, and according to the type of connector used. So the charging classification like level charging, mode charging, type charging, like that we can represent like a level 1, level 2 and level 3. The mode charging like a mode 1 charging and mode 2 charging. Then the type is a type 1 charging and type 2 charging. So here I just want to show you some standards. So here you can see that the charging station type, it may be the AC charging station or it may be the DC charging station. The charging level, it may be the level 1 represents the residential, level 2 represents the commercial, and level 3 represents the supercharger. So the AC supply voltage and the current standards that represents with single phase 120 volt to 230 volt, the current rating of 12 to 16 amperes, and the charger power is 1.44 kilowatt to 1.92 kilowatt. The time taken to charge the battery for charge 24 kilowatt hour battery pack is about, it is taking 17 hours. So coming to the second level charges. So the split phase, that is 208 volt to 240 volt. The current rating is a 15 to 80 amperes. The power rating is a 3.1 kilowatt to 19.2 kilowatt. 8 hours it is taking to charge the 24 kilowatt hour battery. The third one is the DC charging station. That is a level 3 supercharger. So it may be the single phase 300 or 600 volt and 400 amperes. So the charging power is 120 kilowatt to 240 kilowatt. It is taking 30 minutes. Here you can see that the importance of the DC charging, how much time it is taking. So that's why nowadays many researchers, they are giving importance of designing the DC-DC converter and fabricating the DC-DC converter, developing a DC-DC converter like that. So the power from residential level power consumption equal to that of a toaster, 4 miles of your travel as per our I mean the per hour. Overnight charging, but can however could take a level up to 20 hours to completely charge. Here one a charging plug, it is shown J1772 ATA J plug. So here you can see that it contains the how many points. So like a L1, L2, that is a line and a neutral. In addition, the control is also there. Proximity detection is also there. For protecting the vehicle, equipment ground is also there. So this is commercially available. And the charging methods. So coming to the based on the safety communication protocol between the EV and the charging station, these standards are identical worldwide. So we can see that mode 1. Mode 1 represents with home charging plus simple extension card, no safety measures outward. So the second mode 2 represents with home charging with a special cable with overcurrent, over temperature, earth fault, etc. the detection. So this represents with the mode 2 charger and the type of charging based on the type of connector being used. So the Minacus is one of the industry how the connector they are providing. So here we can find it out based on the type of connector being used. The type 1 is used in the US and Japan, ACA. So, and as there are two AC power lines, a ground pin, a proximity detection, and a control pilot signal. So, limited to single phase only because of unavailability of the three-phase power. Charging cable is permanently fixed to the charging station. So, the type 2 is named as a Menacus. So, both the single and the three-phase it is operated, detachable. So, one is interested, you can you can see that. And the benefits and the challenges of off-board charging is less energy kilowatt transfer and problems of battery heating is not concerned. So pilot signal J1172 is used for operation. Weight on EV is added. Slow charging, charging at a low power level. Onboard rectification is used to manage the battery management system. Size and weights rectification due to the EV design. A recharge at any place within the electrical outlet. Protocols concerning communication is not up to standards of industry regarding the charging, the charger interaction. So here you can see that the onboard charger, it may be the like a AC charging. So the onboard charger limited in power due to size reduction and weight reduction. So the entire unit, it is placed in and off-board charging is higher transfer of energy, need to address a battery heating use, less complex BMS system for charging, weight on EVs is removed, fast charging, and charger at higher power levels, more better BMS system, more complexities and higher cost, no flexibility to recharge at various places, responsibility to for interconnect charging goes into the charging stations. So the benefits of onboard, higher transfer of energy, need to address a battery heating issues, less complex BMS system for charging, weight on EV is removed. So fast charging, charger at a higher power level, a more better BMS system. Then the more complexities and higher cost, no flexibility to recharge at various places. Responsibility to incorrect charging goes to charging stations. So coming to the charging stations. So these are the commercially available like a Bharat charging stations. So CHA demo charging stations, Tesla charging station, GBT charging station like this. So this is what the Indian, when we are referring with the Indian public charging standards. So Bharat DC 001, the output voltage is a 40, 60, 72 and output power is like this and the maximum current is 200 amperes. The Bharat AC charging standard 001 that indicates with the output voltage level of 230, output power of 3.3 and a maximum current of 15. So the framework, coming to the framework, the torque density. The torque density is an important criterion of the electric motor. It reflects the volume and the weight of the machines at a given torque demand. Required features of electric vehicle motors are high efficiency, good dynamic performance, higher power density, lower cost. So this is a matter of energy and environment conservation and quality of life. So then we can observe the other features also, like reliability, overload current capability, maintenance free, temperature resistance, fault tolerance. So this states that a matter of safety and life. So we can see that when you are referring with the machine, the electric machine. So electric machine only converts the electrical energy to mechanical energy, or vice versa during the braking operations. During the braking operation, in this regard, people are working with many electric machines like a permanent magnet electric machines, induction machines, switch reluctance motor, like that. So how much it will be the volume, that also it is indicated, torque per volume. And you can see that the torque per volume with respect to the permanent magnet machines only more. So, since the efficiency is also more. And the induction machines followed by the induction machine and a switch reluctance machine. Still, the people are working towards the improving the efficiency of the machine with respect to the nanomaterials. So the nanomaterials offers with respect to higher efficiency, and the framework, one can refer that the electric vehicle, it may be connected to the grid, and it may be connected to the home, it may be connected to the building, or it may be connected to the vehicle to the grid, and vice versa. So here we can observe that the charging of the batteries, it may be charged through the conventional grid, or it may be charged through renewable energy, or the battery swapping technology is also there. So that is the various framework. We can make it like a vehicle to vehicle technology, or vehicle to grid technology, or like a grid to vehicle technology, vehicle to home technology, like that it has been arrived. So here you can see that the simplified diagram with respect to the vehicle to grid. So how it will be? So for example, here through solar energy also it is getting charged, and the solar energy it is feeding to the grid, and through the grid the vehicle it is also charged. So this is also one kind of technology. The grid to vehicle is sometimes during the regenerative braking mode of operation, we require to transfer the power from grid to vehicle. So in this regard, we can see that the importance of the power converter, how it is transferring power from power grid to electric vehicle, or vehicle to electric, I mean the power grid. So we need to have the energy efficient operation, energy transfer operation. For that, the power converter also it must be operated with efficient manner. In this regard, recently developed devices like recently developed devices, um, but like a wide band gap devices, the gallium nitrate devices, or silicon carbide devices, people are started to use. So, and so we can see that the framework we can like a V2X, like any technology we can move it. So in this regard, we need to understand the importance of the power electronics technology. So up to this, any discussion you please. So this is the one of the power electronic technology commercially available. This is a Bell Power Solutions has introduced 22/25 kilowatt bidirectional liquid cooled onboard inverter battery charger with expert functionality. Up to 4 of these charging units can be connected in parallel with the efficiency near 94%. So this unit, it is possible to connect this charger to a charging station or directly to the grid. So the output voltage covers a wide variety of batteries from 240 volt DC to 800 volt DC with a constant 60 amperes output current. When running on battery power, the system can export up to 25 kilowatt to power the three-phase AC equipment. So here we can see that many technologies. So the battery swapping include exchanging an EV charged battery for a charged one, eliminating the need to wait at the station for EV to charge the charge. The business model is based on the leasing, renting, subscription for the use of the battery swapping stations or pay as you go systems for EV batteries. But the pros and cons when you are referring, the advantages we can say that very fast fueling time, whatever the battery size, typically 5 to 10 minutes. So batteries stored in the swap hubs can be used to balance the grid. So the drawbacks is no standard batteries, heavy logistics for car. So I mean the four-wheelers. Battery swap network must be developed at once the high capital expenditure. Cars still need conductive charging just in case more complexity, more fast. So the assessing EV charging demands are the EV charging demand at urban regional level depends on per capita vehicle ownership rates, EV penetration levels, and vehicle utilization patterns. So as it is typically used for public planning processes, such as assessment should be conducted or commissioned by the government planning authorities responsible for charging infrastructure. For estimating the requirements of the public charging infrastructure and EV charging demand, assessment should focus on the projected demand for public charging for different vehicle segments. So this can help to help calculate the number of public chargers required, which in turn can be used to set annual targets for public charging infrastructure. So the provision norms for charging points like 4 watts, 3 watts, 2 watts, PV buses, some standards are already arrived. So the location and the planning and land allocation, that also an important factor. In this aspect, the government has given many guidelines with respect to the installing of the charging stations with respect to the various values of the power. One of the important factor is a site planning for EV charging. Site planning is an important aspects for integrating the EV charging in parking areas. It depends on the type of parking area as well as the number and the type of EV charge points that need to be accommodated at the site. So the space requirement for upstream electrical infrastructure is, so for example, you can see that how much area is required and recommended distribution setup with respect to the various power ratings. And the government policies is also arrived. Many information is also there, like first automotive mission, MNRE incentive scheme for EV, NEMP, like that many NITI Ayog roadmap. That is a good site for accessing many information. PLI scheme, production linked incentive, like that many are there. So I just want to show one case studies with respect to the charging, whatever we executed in our laboratory. Since the time constraint, I just want to execute one case studies. So in this, this looks to be one of the charging, how we are going to use. So whenever I am showing one block diagram, in the block diagram, I have shown with a 2 power converter. This is what your grid. So grid system. And here, this one is the H bridge. And one DC-DC converter is also there. And one battery is also there. So how the power it is feeding from a grid to battery and a battery to grid, those things we were evaluate. So I told you the functions of the first power converter and the second power converter. The first power converter is the AC-DC power converter. Second one is the DC-DC power converter. So this DC-DC power converter, it may be the buck boost power converter. When it is operating as a buck, the DC link voltage is more compared to the voltage across the battery. Then power it is feeding from DC link to this one. That is, a power is feeding from source to grid, a source to battery. So when the boost mode, if it is operating, then the power it is feeding battery to the source. This is the fundamental information. So I told you that the first stage represents with the unity power factor correction converter, and the second stage represents the DC-DC converter. Coming to the control. So with this, one is realizing this represents with exactly the entire unit is E. So whatever the synchronous machine equation, that it is applicable, like E into V divided by X into sine delta. So one is varying the delta, we can change the power from one level to another level. Or if we are changing the delta like a synchronous machine, the delta may be positive in the case of generator and negative in the case of motoring. So like that, if we are changing the delta, I mean the power angle, the power transfer, it will be from grid to battery or battery to grid. That may be possible. This is the simplified structure. In the structure, we can understand the similar way we can develop a lot of structures. So this the first power converter role is maintaining the current shaping is sinusoidal in this point and unity power factor in this point. So that is what the objectives with respect to the AC side. In the DC link side is we want to maintain the constant DC link voltage. So if you want to maintain the constant DC link voltage, VDC reference is there. The actual DC voltage, it has to be sensed and feed it to the error detector, then one controller. The output of the voltage controller that represents the magnitude of the current reference. This magnitude, it will be multiplied by the unity magnitude of the supply voltage, that is sinusoidal shaping, but the peak magnitude which is equal to 1. So that it will be multiplied. Then it is fed to the inner current loop of the controller like a PA controller. Then I mean, this is what the reference, and the actual it has to be sensed through the current sensors. So then the output, it will be fed to the another controller, which is called as a proportional integral controller. Then from this is what the control signal or modulating signal. This modulating signals, it has to be fed to the switch through the control logic. Like when the top switch is conducted, bottom switch, it is not to be conducted. When the similarly S1 and S2 is, it will be conducted diagonally. Then S3 and S4 which will be conducted diagonally. So for this, we need to generate the PWM, like a sine triangular PWM, that it has to be generated. Then it is feeding to the switches like a S1 and S2 for one operation. Then S3 and S4 is for another operation. So this indicates with the unipolar switching. Coming to the controller with respect to the DC-DC converter, I said that when it is operating as a buck mode, the power it is feeding from grid to battery. If it is operating at a boost mode, the power it is feeding from battery to grid. So in this regard, we need to see that buck mode or boost mode and the current rating based on the current, how much current it will be injected to the grid, how much the current it will be, how much current is injected to the battery. That means how much current we are feeding this direction or this direction, that we needed to be tested. So this is what I said. The synchronous machine representation with the infinite bus bar, the same thing only we are bringing as a example representation of the grid. So this is what the leakage inductance which we are connected here. This is what the Vs of T, the entire two battery along with the two-stage power converter is represented like this. So when it is charging, how it will be? When it is discharging, the current, it will be 180 degree out of phase. So when the inductive operation is also possible, the capacitive operation is also possible. When it is inductive operation, how it will be the current? When it is operating the capacitive operation, how it will be the current? So that is a charging and capacitive operation along with the charging, how it will be. Discharging, how it will be. So this is the one of the diagram tested by our MTech student, and through simulation. The same thing he has tested with the experimentation also. And this is the DC link voltage is maintaining constant. This is the at this instant, he is changing the battery current from 10 amperes to minus 10 amperes. So how the battery voltage it is changing, that he has observed. This is the grid voltage and the grid current. This is an expanded view. So here the charging, here it is getting discharging. Here you can see that unity power factor is getting after this time instant. The current is 180 degree out of phase, that we can understand that the current it is feeding back to the source. So under that condition, and we can increase the magnitude also, that is the current injected to the battery and current injected to the battery terminal also, and the current current is feeding from battery or receiving from the grid, that we can change it. So this is the transient response, that one. So under this case, we were tested that the waveforms and harmonic spectrum for discharging case. So that discharging case that represents with the current shaping, it looks to be the sinusoid, and we can observe that according to the grid standard, it will be follows with one finite. I mean, one finite. Then the harmonics, it will be maintained that less than 5%. And so this is the one of the fundamental case studies we were executed in the laboratory, and we were discussed many controllers with respect to the power quality operations also, like with respect to the grid. I mean, when the grid frequency is changes, how the PLL it is getting responded, how the controller it is getting responded. So, we were tested different operations with respect to the grid quality, like unbalance, harmonics, DC offset, phase jump. In this regard, we were tested with yes. We were tested with different PLL, both in the single phase and the three phase also we were discussed. And one of the important thing is we were observed with respect to that indexing, like a DC offset, then harmonics. So how the PLL it is getting responded. So this is the balanced case, and this is the represents with the theta, that the theta decides the output of the controller. So when unbalanced, how the theta it is going to be changed. So we were observed like a fast transient response. This is a conventionally available SRF PLL. So fast transient response under balanced and undistorted conditions. So in this regard, we were developed many, we were found with many literatures. So one can increase the bandwidth and the filtering characteristics, it is going to be reduces. And one of the PLL, we observe that from the literature is a feedback control tracks the single phase, the phase angle and the frequency. So the forward frequency is kept constant and increased complexity in the phase detector section, poor performance for larger frequency deviations unless the compromise is made for filtering characteristics. So the requirements is the fast transient response and good filtering characteristics under distorted conditions. So the zero steady state error and improved dynamic response for large frequency deviations. So in this regard, we were modified with respect to the systems along with the solar. We were verified. Here we were used with battery also. And this is what the response of the feed forward PLL, which we were tested how it will be under normal conditions, the cos theta and theta, how it will be. And response of the feed forward PLL, we tested with unbalanced conditions also, how it will be the cos theta. The unbalancing we were created here. So this is the PLL under harmonics. This is the DC offset we were created, that also we were tested. So the various case studies we tested in the laboratory, but we had a very little experience in using the hydrogen energy. Very recently, one of our faculty joined with the the experience with the hydrogen energy. He is doing extensive research in the field of hydrogen energy also. So I just want to stop my lecture up to this. Any discussion with respect to the power electronic controller which is used for electric mobility, you please discuss with me. Sir?
Participants, any questions? Participants, any questions? Participants, any questions? Participants, you can interact with the resource person. Any questions?
Good evening, sir.
Good evening, sir.
Sir, kindly ask.
Actually, I just want to say one more important information. With respect to the clean energy and as zero environmental impact, which attracts the automobile industries for hydrogen vehicle development. But hydrogen offers several advantages in terms of combustive qualities in in the internal combustion engines. But it requires a careful engine design to avoid anomalous combustion, which is a key issue with hydrogen engines. So the consequence of energy efficiency, power production, NOx emission may all be improved. So the cost and the efficiency of the hydrogen plant are determined by the hydrogen production sources, and the cost may be reduced if the plant is close to the natural resources. So, and therefore the locations of it sources should be considered while developing the hydrogen plant. So the people will adopt hydrogen technology if they are aware of the benefits it provides to the environment and human life. So educating residents about the hydrogen technology is critical in gaining public support for the technologies growth. This is my observation, and in this regard, we can use it comfortably with the battery technologies.
Sir, with respect to safety aspect, which will be better, sir, compared to?
Actually, right now, both are good. But the thing is, at the end, I have pointed out that people will adopt the hydrogen technology if they are aware of the benefits it provides to the environment and the human life. So educating the residents about the hydrogen technology is a critical in gaining the public support for the technologies. But whereas the battery technology already, it is very simple. But nowadays, with respect to the protection aspects also, people are developing tremendous technologies. Then, I mean, with respect to the commercial vehicle, people are moving towards the battery technologies.
Okay, sir. Thank you.
But no doubt, the hydrogen energy is also growing. I said that when I'm starting, zero emission. Many advantages there, but still we have to. There is a good scope is also there.
Good evening, sir.
Good evening, sir.
Sir, actually, I want to know that what exactly the basic difference between hydrogen vehicles, whatever it is coming now, and the EV vehicles, where exactly it differs? Means it changes the battery, replacement of battery or something else?
Sir, energy source only. In one of the slide I have shown in the beginning itself. So we can use a single energy source or multiple energy source. So as you said, the fuel cell is also there, the battery source is also there. So in this regard, you need to use both or separate. I mean the individually, or whenever you require the fuel cell, that time alone you want to operate it. That is depends upon the applications. So for example, if you want to use the fuel cell, the particular power converter you need to be operated, and the power management also you need to be considered. But whereas here, with respect to the battery technology, the bidirectional power flow is comfortably we can operate it.
Yes, that's true, sir. Bidirectional is already there in many places. It is already using.
Yes, correct.
Yeah.
Because this technology is already developed.
Yes, yes, correct. So that hydrogen, so only the change is instead of the battery, they are using the source as hydrogen source, right?
Yes, correct.
Okay.
But
So according
still,
to
people are working towards this technology. I told you, the hydrogen offers several advantages in terms
yes,
of
yes,
combustive qualities
correct.
in internal combustion engines.
Yes, sir. And recently I heard the news like instead of lithium-ion batteries, people are choosing for the sodium-based batteries. So based upon their like advantages regarding the protection and everything.
Correct.
So is there any scope for that one also?
Yes, sir. But people are working towards the materials. They want to obtain, I mean, they want to find it out at the end, the energy efficiency.
Energy efficiency, correct.
Yes, correct.
Okay, sir.
And
Thank you.
emission.
Yeah, emissions both are having nothing, right? Zero emissions only from both whatever the
Correct.
sodium, lithium, and hydrogen also.
Correct.
Yeah. Okay, sir. Thank you.
Thank you, sir. But again, I am telling you, educating residents about the hydrogen technology is crucial.
Yeah, of course. Right now, the service sector is really for EV also very less. So people are now looking for that service
But
sector. So
battery technology is already they are good in battery technology.
yeah, right now they are all good.
We are comfortably operating the mobile phones, correct?
True, sir.
Thank you, sir. Thank you, Senthil sir.
Thank you, sir. Thank you so much. Any further question, you mail me at any time related to the power electronic controllers, because basically I'm a power engineer. We are developing the power electronic controller, EV technologies, and renewable power generation technologies. And we were very recently, we started the research with respect to the heating, welding, and biomedical applications also. So this is for your kind information. And so thank you everyone. I think second speaker is waiting for waiting. Thank you.
Sir, thank you, sir. Lavanya, you can formally conclude. Lavanya.
Thank you, sir, and participants for interacting with the resource person.
Thank you, sir. Can I
I
leave?
hope the participants have got enriched knowledge from today's section. Thank you, sir.
Thank you, sir. Thank you. Thank you, Senthil sir. Thank you very much.